So the phrases domain and range should sound familiar. And most of this lesson is review, although some of the types of questions we'll be asking will probably go beyond what you would have seen in a previous course. But here we have a mapping diagram showing you a relation. And the question is it a function or not? Now, in general, it doesn't really matter what variables I choose, but obviously the most conventional or boring, however you want to look at it, these are my x variables, these are my y variables. And so we can see if x is 1, y is 6. If x is 2, it helps if I get my colors correct. If x is 2, y is 7. If x is 3, y is 7 or 8. And if x is 4, y is 6. And with that said, I can now see quickly that this is not a function. So I'll write that down as clear letters, not a function. Because if a relationship is a function for every input, and quite often we call that x, there should be only one output. And that's if something is a function, we think of numbers going in and numbers coming out. And if we put one number in, we should get only one number out if it is a function. However, right here we have the problem. When x is 3, it's either an 8 or a 7 coming out. Or a little better is when x is 3, it's both a 7 and an 8 coming out. One number goes in, two numbers comes out. So this is a relationship, but it's not a function. And so I'll just kind of state why. When x equals 3, y equals 7 and 8. That's it. What's the domain and range? Domain is a description, and there's many ways of expressing the domain of all the inputs, of all the independent variables, of all the x's usually. And so the domain in this case is just the set of 1, 2, 3, 4. And so I'll just make a list, 1, 2, 3, 4. I shouldn't say all the numbers from 1 to 4 because it's not including the rational numbers between 1 and 2, for example. And the range is just a list of all the outputs, or the dependent variables, or the y, which is just 6, 7, and 8. And again, it's a discrete list, just these finite numbers. All right, so now let's look at functions that are a little bit more complex. And here I want to find just the range of these two functions, but they're quite similar. They're both set up they both involve minus 2x squared minus 2x, which is what we call a quadratic function. But f of x has the restriction where x is only less than or equal to 0. And without that restriction, that means right here we're saying x can be any number. You can put any number in, and this tells you what numbers come out. However, there's this restriction here. So we can put any number we want in as long as it is less than or equal to 0. And then over here, for g of x, same initial function, but then the restriction on it is that it can only be numbers greater than 0, not equal to. So these are two similar but definitely different functions. And I want to know the range of each. The range is a description of the values that come out of a function, of the y values. And one great resource, especially with functions like this that are a little bit tricky to visualize right away, especially since we haven't really covered quadratics yet, is just to take advantage of graphing technology to graph each. And so I'm just going to use Desmos again. And so I'm going to graph. If I look right here, first I want to focus on just minus 2x squared minus 2x. Which I see right here. Now this again is not either f or g. This is the entire function. So I only want to pay attention for function f. I only want to pay attention when x is less than or equal to 0. So what does that look like? Well, first let's visualize it here before I actually show you. Because on most graphic calculators, you have to just look at something like this and then understand the range or the domain yourself. And so we want to think about where is x at 0. That's the sort of boundary point. And so I can see x is 0 right here at 0, 0. And so I want to imagine what does this function look like if only x was 0 at most or anything less, which is, I'm really visualizing this whole region here that I'm tracing, which goes down forever, goes up, reaches this vertex here, and then stops right there. That's the region we're visualizing for function f. And so ideally, we can already kind of see what that looks like without me having to explicitly show you. In Desmos, I can quite easily show you, though, by just adding some curly brackets here and saying where x is less than or equal to 0. And this is ideally what you've been visualizing anyways. And we can see the whole graph. So the range of this are all the y values. And so the y values, or the outputs, I can see reach a maximum, a highest point of 0.5. This graph never has any y values bigger than 0.5, but it goes down forever. I mean, I could just go down for a while, but I'm obviously not going to go down forever. And so the range of this is everything from positive 0.5 and down. So everything less than positive 0.5 or equal to positive 0.5, because it does reach that point. It doesn't matter the graph stops right here on this side, because on the other side, it just keeps going down forever. And so the range is everything less than or equal to positive 0.5. There's many ways I can write that. And we don't want to get too hung up on any particular way of writing it. But we do want to be hung up on understanding different ways of it being expressed to us. So the range of f of x. What I personally like best is just this. Y is less than or equal to 0.5. That's great. And an IB examination, you're fine with stuff like that. If you want, you can make it look a little more fancy and complicated by putting all the other notation around. You may see this, where we can say the range is a set involving the variable y, where y can be any real number. However, any real number only from where it is less than or equal to 0.5. That's a bit more messy looking. It's perfectly fine. Again, it's really just this part that is the most important part. You also learned before, though, however, what we call interval notation. And for example, I can also express this as everything from negative infinity up to 0.5, including 0.5, but not including negative infinity. The round bracket indicates that we're not including that because you can't actually include negative infinity. It's not a number. You can't reach it, but we are including the number 0.5. However, another notation that I'm not as big of a fan of, but you may see on an IB examination, is instead of those round brackets, we use a backwards square bracket. So by that I mean it looks almost the same as before. So negative infinity 0.5, and that sort of square bracket there, which should be familiar from grade 10 math, is identical. But on the left-hand side, instead of using a round bracket, we use another square bracket, but the reverse of what we would normally use. This all means the same thing. Personally, I like this the best, and this is okay, and I'm like, meh. But I understand it all, and that's the key. You want to understand it all as well. So for g of x, the range. Same graph, but we're looking at a different part. And so if I go back to the graph, I want to now visualize basically what disappeared last time. And hopefully you can already kind of see it, because I did show the entire graph before. But to kind of make it more explicit, this is what we're looking at, just this part here, in which it goes down forever, and the highest point it reaches is almost 0. I say almost 0 because right at 0, the function is undefined. When x is 0, it's not defined, because if you look at my restriction, it's just where x is greater than 0. So when x is actually exactly 0, there is no graph there. That's why in Desmos you see that little open point. But as soon as I get a little bit into the positives with x, my graph exists and goes forever and ever and ever and ever. So here the range is not everything less than or equal to 0, because my y never equals 0. It's everything just below 0. And so my y is everything less than 0. And that's what I prefer, and that's what I'll write down first. So for the range, y is less than 0, not less than or equal to. Now again, I could do all this other stuff right here, and I'm not opposed to it, but I'm feeling lazy, so I'm not going to. Or using the other notation, if everything's less than 0, that means y can go down to negative infinity, which just means forever down, and it reaches 0 at the max, but doesn't actually quite reach 0, it gets infinitely close to 0. So using the notation you're probably more familiar with, I can go negative infinity up to 0, both with round brackets. Or if I want to use the other notation, which again, we want to be familiar with, you don't have to use it on your own if you don't want, but you should be able to understand it, is I have 2 round brackets here, so it's going to be, again, very similar. Not an 8, though. But instead of both round brackets, both will be square brackets, but the kind of reverse of normal. So like this. All great. You can even use words on an examination. You can even say the range is all values less than 0. You can just say that, all y values less than 0, and that's totally fine. All right, last one, I got function h. I want to determine both the domain and the range of function h. Getting increasingly complex function, and you're always encouraged to use graphing technology in this course. This course is about applying ideas using technology. So I'm just going to go straight to graphing this function h. And then I'll connect it to some of the algebraic ideas behind it as well. So let me get rid of this. Let's reset this. And so function h is y equals 1 divided by the square root x cubed plus 3. plus 8, sorry. All right, so this is my initial graph. And keep in mind, I can zoom out. And one thing I can see right away in terms of the domain is that this graph does not go forever to the left and right. It definitely seems to go forever to the right. So as x gets larger, it goes on and on and on. It definitely doesn't seem to exist over here at all. As well, it definitely seems to go up forever, but it doesn't seem to go below the x-axis. Now in Desmos, it's really easy for us to zoom in on parts. On your graphing calculator, it's more time consuming. But I can definitely get a sense of things here. So from the graph, if I look at domain, it definitely goes on forever. That's very, very clear. And on a graphing calculator, if you just change your window settings, which you should always do, you can see that it'll just keep going on and on forever to the right. So it goes forever, it goes towards positive infinity with no end. On the low side though, it seems to approach this -2, but doesn't ever seem to quite reach it. And if I, for example, if I just move up really high, it looks like it's at -2, but if I zoom in, it's not quite there. It's really close, but it's not quite there. And so I can get a good idea just from the graph that the domain is everything more than -2, everything greater than -2, or from -2 up to infinity, but not including -2, and definitely not including infinity, because again, infinity is not a number. So while I will write that down, I want to show you how we can get a sense of this algebraically. Although again, looking at these graphically is a key idea of this course. So I'll say the domain. There's lots of ways I can write it. I'll just write it as x is greater than -2. That's because you don't have to show it in more than one way. However, from an algebraic standpoint, let's understand why that is. If I look right here, why can't x actually equal -2? It gets really, really close, but why can't it equal -2? Well, notice if x equaled -2, then right here, x cubed plus 8 would become -2 cubed plus 8. And what is -2 cubed plus 8? Well, -2 cubed is -2 times -2 times -2, which is -8, plus 8, which is 0. And so when x is -2, I have the square root of 0 down here, which is okay. You can square root 0. The square root of 0 is 0. The problem is then I have 1 divided by 0, and that's a problem. Division by 0 is undefined. I can't take 0 and break it up into, I can't take 1 and break it up into 0 groups or groups of 0 size, right? Division by 0 is not defined. And that's why my graph doesn't actually exist at 0. As well, when x is less than -2, so let's say, I don't know, my example is -3, for example. Notice what we get then. For example, for -3 plus 8, I get -27 plus 8, which is -19. And the problem is the square root of a negative number is not a real number. And that's why my graph doesn't even exist to the left, because as soon as x is less than -2, this whole thing kind of falls apart. And so this explains why my graph never quite reaches -2, but gets really, really, really close, infinitely close, and why it doesn't exist at all to the left of that. Although I don't have to understand that if I can visualize this properly on my graph. Similarly for the range. Let's go back to the graph. For the range, I care about y values. And again, it's pretty apparent pretty quickly that it just keeps going up forever. There's no limit to how high it's going. It's definitely not going down forever. And if you zoom in a bit and notice, it never actually reaches the x-axis. And again, I will explain why this is algebraically, but we can see that the y values never quite reach 0, but they get really, really close, but they go up from there forever. I'll just kind of go back to my basic zoom setting. And so the range is everything greater than 0, not greater than or equal to, everything greater than 0, because again, this graph never quite touches the y-axis. Now in later parts of the course, we'll learn about things called asymptotes, which are visual representations of graphs like this, where they get infinitely close to a number and go forever towards that number, but never quite reach it. Right now, I'm not going to worry about that. However, again, I would like to just mention to understand why the range must be greater than 0, but it can never actually equal 0. And again, if I look back here, for this to equal 0, if it was possible for this to actually equal 0, we can see it gets really close, but how do I know it doesn't ever equal 0? Well, I know it can never equal 0 because you can't go 1 divided by a number and get 0. That's not possible. You can go 1 divided by a number and get really close to 0. For example, 1 divided by 1,000,000 is a number really close to 0. You're breaking 1 up into 1,000,000 pieces. Oh, here comes an announcement.
Good morning.
Good morning. Good morning.
Any staff who are in the building,
That's me.
you may come to the Grand Commons to have your photo taken.
That's great.
Any staff in the building, please come to the Grand Commons for your photo. Thank you.
Glad you heard that. And so this idea that, you know, with division, you can get 0, but the only way you can divide something and get 0 is if you're dividing with 0. 0 divided by any non-zero number, 1. That equals 0. 0 divided by 1,005, that equals 0. But if you have a non-zero number divided by something, you're never going to get 0. You can't take 1, divide by number, and actually get 0. You can get really close to it, but you can never get 0. And that's how I can just see, without even graphing anything, that this function, I can understand why the y values, the outputs, the range, gets really, really close to 0, but it can never actually equal 0. Because 1 divided by, I don't care what you go do with, 1 divided by anything will never, ever, ever equal 0.